Okay, now we're ready to model the I shouldn't say model the SIR model. We will use the SIR model to add a vaccine. Things are going to get good. All right, so one thing you'll notice, we want to have the code that we had been working on, which we had entitled the SRI model. We want to have that pulled up. So if you haven't done so, pause and have that pulled up. But you will notice that I've added a nice little feature down here in the lower right of the figure window. It's called a legend. There are three curves, and we're going to be adding more. So when you have a lot of different colors on the graph, it's really nice to know what they are. So you can see the order. Well, let's first of all look at the legend statement down here in line 69. So we can see this legend statement right here. It's a two-line statement. I put a ellipses in the middle to indicate that it was continuing down on the next line, just because it was getting a little bit long. But the way you add a legend is you type this in, all right? So what it's looking for first are strings. That tells it to use the letter I. I could have spelled out infected, susceptible, and removed, but that just seemed a little bit long. We all should know what the S, I, and R are. So I just put them in as letters to be short. And then I told the program where to put the legend. So southeast, south means bottom. East means to the right, if you're thinking of a map. And outside made it so it's not sitting on top of the graph. Sometimes the legend gets in the way. So I put it outside of the figure, and that will keep it from getting in the way. Now there is a problem with this. So add that to the code before you save it under a different name, because that would be very nice to have in your SIR model. The thing I don't like about the legend is it is an ISR model. So I would like to have it as SIR, but you need to put them in the order in which they were plotted. Okay, so we know the red is the infected line, and that was the first thing we plotted. So I had to put I first. Blue was the susceptible line. I had to put that second, and R was the removed line, and I had to put that third. Now what I really want to do is make this S, the first one S and the second one I. If I run the code now, it will give me SIR down the side, but the colors are all wrong, okay? The red infected curve is being labeled as S, and the blue susceptible curve is being labeled as I. So what I need to do is go back to the plot statement. It would be nice if I had kept them in order. So what I'm going to do is I'm going to move the red infected plot. I'm going to cut it, and I am going to paste it after the blue line. So I want the I to be the second thing. So let me back that up. I want the the S to be the first thing. You can see I have SIR nicely lined up. I'm going to need to back this one up though. Can't have a parentheses with nothing after it. So now I'll have the line 60 is S, 61 is I, 62 is R. So these are in the order that I want them, so that when I run it, I now have blue, red, then magenta, and those match up nicely. We're going to be adding an E at some point to all of this, so we will want to have it as SEIR. So let's plot it like that. Now that we have that in there, so I wanted that into my SIR code. Let us rename this. So let's save this as SIR, and then we'll have VAC for vaccine model. So we're going to have the SIR VAC model, and let me save that. Okay, so what are things that I need to add? Okay, so when we were looking at that flow chart, there was another constant that we had to have in there. and this was the dV dt. Remember we said that would be constant, so I'm just going to call that dV. So this tells me the rate at which I'm going to vaccinate the population. Now remember, everything right now is as a proportion of the population. So let's say that we can vaccinate 0.000, okay, so that would be 0.1% of the population every week. So we're doing everything on a week scale. Okay, so we'll just start out with 1/10 of the population being vaccinated every week. Now, ideally, the CDC would target people who are at higher risk for infection and not target the low risk people. If you live on a cattle farm in Wyoming, you probably aren't going to encounter that many people. Your risk is much lower, you know, but the doctor who's working in the emergency room or the ICU probably should be vaccinated first. So the model simplifies things a little bit in that we're just going to assume everyone is equally exposed, and so it doesn't discriminate between who gets the vaccine and who doesn't, whereas if we have a limited supply, we will target people. So this is the vaccination rate. In, you could say people, or percent per week, or proportion. Okay, so that's what we want to do for that. Okay. Oh, before we do that, we need to change the name up here. So I should have started at the top of the code. It's a little later in the day. I feel a little tired here. So I've renamed it, and I should always start at the top and keep going. The comment should be changed with a vaccine being administered. Okay, so we now have our DV, the vaccination rate, in there. We still want time to work the same way. We get down to plot choice. We're still going to want to plot the same thing. So we're not going to plot how many people have been vaccinated. That would just be a boring linear plot because we vaccinate a certain proportion of the total population every week. And so that's not going to be interesting to look at. Then continuing down, so we don't need to do anything to our plots this time. We're not going to keep record of V, so we don't need to create any new vectors of values. So initializing vectors will all stay the same. We still have S, I, and R. And you know what I'm going to do right now, just because it is annoying to have the ISR, even more annoying to have the IRS. But let us not go there. Maybe somebody's parents work for the IRS, so I should probably not joke about that. So here we go. The SIR model, the zeros are all lined up in the order we know. So now we have S is still equal to 1 minus, so we're down in the calculation loop. Remember, this loop is that's the engine driving the whole machine. So all of the math is happening here. Okay, so we have to put our differential equations into this. So we said we're not going to use a differential equation to calculate the S. We're just going to take 1 minus I minus R. You're either in the SI or R pool, so that will again work. DI, nothing changed actually with the DI, because remember the vaccine bypassed the I, so we still had AIS feeding in to the I pool, and we still had BI coming out of the I pool. All right, so then the next line of code simply adds up, it's the accumulation of infections. When DI is positive, we'll be adding on to I, and when DI is negative, we'll be taking away from I. So remember, once we went to the SIR model, we are at times, we have this negative sign right here, so at times we are taking away from the infected pool, which is why we can have this curve that goes up and then down, unlike our SI model or our I model, where it could only go up. Now, DR has been changed. So remember, there are two ways to get into the R pool. One is the BI, that's leaving the I pool and going into, so you can see the negative BI up here, that when you leave the I pool, you enter the R pool. But the other way to enter the R pool was to put plus dV, okay? Now that's the rate at which we are leaving, that's dV dt, all right? So in order to get how much that changes R, we have to multiply that by dt, okay? So our time periods aren't actually a week, and so dV is measured in people per week. But remember, we've broken this down into very small time bits. So our DR isn't happening over a week, it's happening over a small fraction of a week. So we need to multiply dV times dt to get our DR value. And then we get the total R, the cumulative R value, the way we did before. So really the only thing we needed to change in the code, in the brains of this, was right here. The differential equation for I stayed the same. The S equation stayed the same. The differential equation for I stayed the same. So the only thing that changed was the differential equation for R. But that's going to have a large effect on what happens. Okay, so we once again initialize, give our first S value, and then we said the plots are going to be the same plots that we had before. So with the same variables in place, I'm going to run it now. So this is the old model where there was not a vaccine. And let's see what happens when we run it. Probably we'll get an error, but let's see. It worked. It worked. Okay, so what we can see, the way we can see a difference is we can take the vaccination number and keep playing with it. So it had been 0. We make that 0.000, and when we run it again, watch the peak of the infection curve. I don't see a difference. Okay, now let's ramp dV up a little bit. Okay, so 0.01 or 0.001 didn't do much. So let's try 0.01. So we're going to vaccinate 1% of the population every week, and let's see if that changes things. I don't see a change. There may be an error in our code. Let me pause this and see if I can find the error. I did find the error. This right here, we were finding dr dt, not the amount that dr has changed. And you'll notice in the next line, we do dr times dt. So I was multiplying by a very small time increment twice. So I need to get rid of the multiplication by dt, because if you remember, dr dt was equal to bi plus dv dt, and we don't want to multiply that times dt. So let's get that out of there. And now we might see a change. So dv, we're vaccinating 1% of the population every week. So let's look at the graph when I hit run. Wow, that changed things by a lot. Okay. Now we also have a problem here. The susceptible numbers, all right, and the recovered numbers are actually too low and too high. You can see the S curve looks like it goes down below 0. We can't have negative people susceptible. And then we'll actually send the infection pool going the other way back to S, if that's true. And we can have the recovery be more than 100%. So one thing we could do is we could just stop it at some point, like we go to 30 weeks. We did a full year, but at 30 weeks, if we were to stop this, it all works more or less, although our susceptible population looks like it went down below 0 somewhere before that. Okay, so we obviously can't have less than 0% of the population be susceptible, so we would need to go back further. All right, now a way we can take care of this is if the susceptible population goes below 0, we want the dV to actually not be adding people to the recovery pool. Okay, so let me state that again more clearly. Right at this point here, it looks like about 28 weeks in, our vaccination program should be over. We have already vaccinated everyone who is susceptible at that point. So if we keep vaccinating people, we have more, we're clearly vaccinating people who weren't susceptible to the disease, which, you know, maybe you vaccinate some of the people who have recovered on their own already. It wouldn't be terrible to go past it, but it costs money to vaccinate people. So we don't want to keep vaccinating people. So in our calculations, we probably need an if statement. We change the R, and we want this to happen if S of, oh, that's a capital S, we made SIR all capital, if S of IT is greater than 0, not even greater than or equal to 0. If no people are left to be vaccinated, we want to do this. If they've all been vaccinated, then we don't want to add the DR, we don't want to add on the, ooh, let's see. Actually, I need to move that up a little bit higher. Let me cut that out. It's before we find DRDT. DRDT depends on whether we've already vaccinated everybody who needs to be vaccinated. So if S of IT is greater than 0, that means we have people who should get vaccinated. Then we want to use the line of code that we just had, all right? And if they, let's get rid of the else down here. The else would be everyone has been vaccinated. So we could add that in. Let's say the else everyone is vaccinated. We don't want to keep vaccinating people once that happens. So if that's the case, we need a different DR. DR should equal just the first term of this. And let's indent this. Later on, we could indent that further. So we do want B, people can still leave the infected pool. So that's B times I of IT. They can leave the infected pool, but they're not going to get the vaccine, so we won't add on the plus DV. And we'll end that. So this little string of logic, if there are people to be vaccinated, we'll add the vaccination rate onto the recovery rate. But if we, or the removed rate, I should say, but I should put semicolon at the end of that, make it have a green box in the edit window there. So we won't add on the DV if everyone has been vaccinated. And then in either case, we're going to add DR, DT times DT. Okay, so we're going to add this second term will tell me how many more people have been removed from the infected pool. Okay, or removed from the susceptible pool. So it's the total number of people who have moved over into the removed pool, and we're going to add that to what we already had. So we still want to do that. So let me just highlight those changes. The changes were right here. We have to distinguish between whether everyone has been vaccinated or not. Okay, so let's run this. Much better, much better. So you can see S did not go below the axis. All right, so S is still up at 0, and we did not remove more than 100% of the people from the population. All right, or more than, 100% of the population has not been removed, more than that. That makes sense. Now, I just realized as I was looking through the code, I got a little bit sloppy here. We should label these cases. So this was plotting the S graph. Case 2, let's just say S versus T. Case 2 was doing, that was where we plotted I versus T. So that's that plot. Case 3 is, we're going to comment in that it's R versus T. Okay, and case 4, we're doing SIR versus T. Another space in there. So this tells me when I'm just flipping through the code what these different cases actually are. I should have had that labeled before. Okay, so now we can play with the code and see what happens as our vaccination rates change. So let's drop the vaccination rate way down, 0.001. So now we're doing 1/10 of the population every week instead. And let's see what happens. Okay, and let's take this out to a year. So we can see it looks like that infection curve got much taller. But let's take it out over the course of a year. Okay, so we have an infection curve that seems to be peaking around 17 weeks or so, and it's up there around 40%. Let's put some more vaccine in. Let's go to 0.005. So that's 0.5% of the population every week. Okay, so you can see the infection curve went down. That's one of our goals, is to drive that infection curve down. And we did that, and it looks like we maybe pushed it out in time just a little bit, but not too far. Now let's go up to 1% of the population being vaccinated every week. Okay, you can see that we're driving the infection curve down as we vaccinate more and more people. It does look like it's shifting to the right, but barely. Let's do 2% every week. Okay, that really flattened out the curve. If we could give the vaccine to 2% of the population per week, the curve's getting much, much lower now. Okay, what if we could do 5% of the population? That's probably not likely that we could get that much vaccine out that quickly, because as soon as we make it, we want to get it out to the population. Wow, so if we could do 5%, we basically kill the infection entirely, and everyone goes right to the removed pool, and it would be, they're removed for all the right reasons. We bypassed going through the infection pool, and we went right from being susceptible to being removed. So that's a great scenario right there. If we could do 5% of the population every week, that would be a great scenario. What about 2%? Not bad. We keep the infection rate down under 20% at all times, which is still high. We would be in trouble if that many people were sick, especially if a lot of them had to go to the hospital. So we want to be able to get that vaccine out there quickly. But here's where, when you have the vaccine, let's say we can only get it to 1% of the population each week. So let's put that back in there. Here's where our social distancing comes in. If I can get my A value down ever so slightly, so that just means being a little bit better, we're being a little bit more careful. Look at that, we do two things. We drive the peak down a little bit, and we make it, push it further out in time. We have more time to prepare. Let's go down to 0.6. Wow, so when we get down, if we can take it down there, that made a big difference in the number of people who will be infected at any given time. We're getting people over to the removed pool from the susceptible pool before they have to go in through the infection pool. Let's just go down one more increment. If we can slow it down, if we can, wash our hands a little bit better. Wow, we really flatten out the curve. So this gives us hope. We can bypass having to go through infections, and we can really level that infection curve, which will take the pressure off of hospitals. But this, remember, requires having a vaccine. So we need to be able to push out in time. We need to keep our infections low while we're developing the vaccine. If we can also, there's the other thing that we can do. Let's raise A up a little bit. If we can develop other medicines that help combat it and get people out of the infected pool and into the removal pool faster, that was the raising this. Let's make that a 0.4. that also really flattened the curve because we're keeping the infected pool smaller while the vaccine is being administered. So that makes a big difference as well. So a combination of developing medicines and vaccines and us lowering the A value by our social behaviors and our health behaviors, all of those combined can help us to fight virus and be able to make it through. All right, let me stop the video.